Okay. Okay, finally, a short chapter, so chapter 16. Okay, chapter 16.1. So especially 16.1, you should already know all these things. Okay, so I'm gonna hold you guys responsible for like all these things. Okay, the red blood cells, etc. The types of white blood cells. Remember that the mnemonic for this actually is never let monkeys eat bananas, and so that not only does it tell you the types of red blood cells, it actually is in order of most to least. Okay. Okay. What else is there? Okay. Chemical composition of blood. Okay. Okay. You definitely have to understand hematopoiesis or hemopoiesis. Okay. You have to understand the factors that go into it. So EPO, erythropoietin, thrombopoietin, okay, and leukopoiesis, okay, okay, okay. You have to know what a CBC is, okay. I'm sure you guys heard the term before. If not, you should know what CBC means and what mean corpuscle volume is and what mean corpuscle hemoglobin means. Okay. Also, you should definitely know what hematocrit is. Okay. What hemoglobin level should be, and that's it. You don't need to know the white blood cell count and red blood cell count, but you should know what hematocrit is and what hemoglobin is. Not only what the definition is, but what the percentages should be. Okay. Again, you should know what you don't have to know the difference between males and females, and there really isn't any here. But you should know what the ratio, what order they come in terms of percentage. Okay. Here, the neutrophils are generally listed as 70%. The lymphocytes are usually listed as 20%. That's in a normal, healthy human being. Okay. If a human being has an active infection, then yes, that will go lower. So neutrophils will go lower because the lymphocytes will go higher. There'll be more of them. Okay. Okay, so mature red blood cells can lack a nucleus. Okay, so red blood cells, the way they form is they have a nucleus and they grow and they grow and they grow. And in the very last stage of the process, they lose their nucleus. Okay, and that tells you a lot. Okay, the morphology of the mature red blood cells can provide clues to the presence of disease, especially something called mean corpuscular volume, the size of red blood cells. Okay. So there's two things that can go wrong. One is that the cells get too big, or two, the cells are too small. Okay. So too big, macrocytic anemia. Okay, the white blood cells are too, or not white, the red blood cells are too big. Too small, microcytic anemia. Okay, the cells are too small. Okay, those two are both anemias, but they both tell you something very different about what's going on in the patient. Okay. Okay. Okay, and the last term is aplastic anemia, simply not enough red blood cells. And we'll get to that in a second. Okay, not enough production of red blood cells. Sorry. Okay, so clear that up. So this is a red blood cell. Okay, you should know the shape. This you should know from biology, anatomy, etc., etc. Okay, hemoglobin plays a huge role in oxygen transport. Okay, there are 4 globin molecules in normal humans. Both of them are 2 alphas and 2 betas. Okay, fetuses have something called gamma globin, etc. So, okay. Okay. Red blood cells live for about 4 months, exactly 120 days, which is why when you go to the doctor and get a H1C count, um, it tells you your sugar levels for those 120 days, how much glucose is stuck on your red blood cells, right? Okay. Uh, okay. After 120 days, the older red blood cells rupture or are phagocytosed in the spleen. Okay. They go to the spleen to die. So spleen is a red blood cell graveyard. Okay. The remnants, so you get the blood cell is broken down, you recycle the heme, okay, you recycle the iron. The remnants of the heme are then converted to bilirubin and excreted as bile. Okay, bile is used for digestive process. Bilirubin metabolites are excreted in urine. That's what makes urine yellow. Okay, jaundice results from elevated levels of bilirubin. Okay, so if you have a whole bunch of red blood cells rupture, okay, then you can get jaundice. Okay, all right. Red blood cells disorders, decreased oxygen transport. Okay, anemia is when the hemoglobin level is too low. Okay, so hemolytic anemia. Okay, sickle cell disease, um, hereditary spherocytosis is where the cell is circular shape, and if it's circular shape and not that weird disc shape, then it's easier to explode. Okay, sickle cell disorder, which I'm sure you guys have heard of, iron deficiency anemia, not enough iron in your diet. Okay. Okay. I don't know why polycythemia vera is listed under anemia. It's not anemia. It's actually the opposite. Polycythemia, many cells. Polycythemia is where you have too many red blood cells in your bloodstream. Okay, and that causes bad effects too. Causes increased risk of clots. It makes your blood thicker, which makes it harder for your heart to pump it, and it causes you can lead to stroke and organ damage because the blood's too viscous to flow through the capillaries. Okay, so this is hemoglobin. So in normal cells, mostly, not all, but mostly alpha and beta chains. Okay, and in the middle is a porphyrin ring that holds the iron. The iron is actually the ultimate thing that holds the oxygen. Okay. Okay. So iron is ingested from the diet. You absorb the iron through active transport. You transport the transferrin transports the Fe in plasma. Again, you do not want free iron moving around in your bloodstream. That is extremely, extremely bad. Okay, any iron you have needs to be sequestered. Okay, so as soon as you have iron is sequestered. Okay, transferring ferritin are needed to protect the iron. Okay. Okay. So iron goes into making heme, okay, and it's pumped into red blood cells. Some of it gets, as the red blood cells die, some of the spleen takes care of the old ones and converts the heme group to bilirubin. The iron gets recycled. Okay, some of the iron gets lost in the feces and stuff like that, but most of it gets recycled. Okay, and then yeah, that's the bilirubin metabolites and stuff. Okay, all right. Okay, so there are two general cases of anemia. Okay, either you're not producing them fast enough, or you're losing them faster than you're actually producing them. So it's like you have normal, which is input and output are roughly the same. Okay, and you can either increase the output, increase the death, or decrease the input. Okay, so accelerated red blood cell loss or accelerated not just blood loss, but red blood cell loss. So you can have blood loss, okay, which will lead to cells are normal size. The hemoglobin is but lower in number because they don't fill up with enough hemoglobin. Okay, hemolytic anemias are where hemolytic, right? So the red blood cells lyse. You have hereditary ones, membrane defects or enzyme defects, okay, or sickle cell anemia where it changes shape, okay, or you can have them acquired. The most important one out of the cases is parasitic anemia. The malaria parasite gets into the red blood cell and they pop them open all at the same time. And usually what happens is you have a sudden lyse of red blood cells, which leads to a drop in red blood cell count, which leads to chills. Okay. All right. Drugs, autoimmune reactions also occur, but the most major one, and the one that I want to make sure you guys understand, is parasitic. Okay. So these guys, what you will see, okay, micro sick. Okay, the cells that come out, it are usually will be smaller. Okay, it's not true for malaria, but for other ones, okay, because they're rupturing and therefore you're trying to rush the process. Okay, all right. Aplastic anemia. Aplastic anemia means you are not making enough blood cells, red, white, okay, both. Okay, you're just not making them fast enough. Okay, iron deficiency and folic acid and B12 deficiency. Okay, iron deficiency. You need iron. Everybody needs to take a certain amount of iron every day. And usually it's easy. Okay, iron is not really that hard to get resources on, especially if you okay if you're vegan, then you have to look for iron a little bit. Okay, folic acid deficiency and vitamin B12 deficiency. These two are the enzymes, not enzymes, sorry, cofactors that are responsible for DNA synthesis. Okay, not enough DNA synthesis the nucleus keeps producing proteins. Okay. Before replicating, and therefore you end up with macrocytic anemia. Okay, the red blood cells end up being too big because they take so much time for DNA synthesis that they grow too big. Okay. Inadequate production of EPO. So you should know that, right? So EPO stimulates red blood cell development. So not enough EPO, then not enough red blood cell development. Okay, platelets are cell fragments from megakaryocytes. Okay, they're smaller than red blood cells. They don't really do any. They contain mitochondria, smooth ER, granules, something like that. So they're important for blood loss, immunity, and inflammation. Okay, so this is an active platelet. You see they're about 1/10 the size of a red blood cell. Okay, so usually they're all smooth. But when activated, they get spiky. And when they get spiky, they kind of, instead of flowing past, so circles flow past each other really easily. Okay, this shape thing, the spikes do not. Okay. Okay, so if I, stab one of you, the first thing your body tries to do is hemostasis. Okay, blood clotting, because you don't want the blood, too much blood to leak out. Okay, vasoconstriction, the platelet plug begins with platelet adhesion. The exposed collagen and tissue lead to a clot, and that leads to a coagulation cascade and a thrombus. Okay, blood clot. Okay, so platelets activation begins the clotting process. The platelets stick to collagen in damaged vessels, and then they also respond to hemoglobin factor in damaged vessels, and that causes release of platelet activating factor. Okay, thromboxane A2, and lastly prostacyclin, and you'll see what those do. Okay. Okay, so damage to the wall of the blood vessel exposes collagen. The platelets adhere and release platelet factors that accumulate and picks up more platelets. So you can see this is a positive feedback response. Okay, this leads to a very temporary platelet plug, so temporary hemostasis. Okay, so along with the fibrin coagulation cascade, which we'll get to in a little bit, okay, you form then a more permanent plug, okay, and then eventually you need to remove the clot. So the fibrin is slowly dissolved by plasmin from the platelets, which then dissolves the clot, and then by that time you should have enough time to repair the tissue. Okay. Okay. So things that are important here. Okay. Okay. Collagen. So activated. Okay. Hemoglobin factor. Okay. thromboxane. Okay, these three primarily in PGGF, these three actually cause the first plug, the platelet plug. Okay. All right. These four, sorry, not three. Okay. The next thing, the platelet plug is a temporary plug. Okay. It's not a clot. Okay. So next thing is the coagulation converts a platelet plug into a clot. Okay. And there's two pathways. Okay. The intrinsic pathway and the extrinsic pathway. Okay. And then they both converge on what's called the common pathway. Okay. So the intrinsic pathway, the extrinsic pathway. Intrinsic pathway is contact activated. Okay. The collagen and other cofactors that are in the platelet cause factor 7 to activate. Factor 7 activates factor 9. Factor 9 then activates factor 11. Oops, factor 11 activates factor 9. Okay, factor 9 then activates factor 10. Okay, the bad thing about this cascade is the factors are not in order. They're not in order because they're named in an order that they were discovered, not the order in which they're used. Okay. Okay. But the more important thing is the common pathway. The common pathway starts with the activated factor 10. Okay. Factor 10 cleaves prothrombin to active thrombin. So now you have an active thrombin. So pro is inactive. Okay. The thrombin cleaves fibrinogen into fibrin. Okay. Fibrinogen is completely soluble in the bloodstream. Fibrin is completely not. So cleaving the thrombin, cleaving the fibrinogen into fibrin makes the tissue, okay, makes the fiber come out of solution right then, right there. Okay. And then you have factor 8, which cross-links the fibrin. So instead of forming just lines, they form crosses. And these cross-linking captures all the white blood cells and white blood cells. And that is a clot. Okay, that is a clot. Okay. Okay. So once you have a clot, you have to break the clot. Okay, eventually. And so not right away, because that would make it useless. Okay, but eventually your platelets secrete plasminogen, which then activates plasmin. Plasmin chews away the fibrin polymers, and that releases the clot. Okay, there is an enzyme called tissue plasminogen activator (TPA), and that also helps break apart the clot. TPA you might have heard of is known as a clot buster. It's what they inject into you for a heart attack. Okay, it hopefully breaks the clot. Okay. Thrombus is a blood clot that adheres to a damaged blood vessel. Okay. Two mechanisms limit the standard clotting. Okay. The inhibition of platelet adhesion and then the inhibition of the coagulation cascade and fibrin production. Okay. So these are also known as anticoagulants. So I'm sure you've heard of these before. Heparin, clofibrin, antithrombin 3, Another example of an anticoagulant is warfarin, or otherwise known as Coumadin, um, and that is also an anticoagulant. Okay. Okay. So here, the regulation partners better. Okay. Uh, okay. Okay. So endogenous factors that you should know is here. Okay. CPA. Okay. Uh, prostacyclin. Okay. So there is a thing called prostacyclin thromboxane ratio. So one creates plots, one releases plots. So the ratio between the two is how is basically controls your clotting. Okay. Okay, that's it.